Have you ever stretched a rubber band or pulled on a spring? You might notice that they stretch and then return to their original shape. This fascinating property is called elasticity. Elasticity is the ability of a material to return to its original shape after being stretched or compressed. Imagine a spring attached to a ceiling. When you pull the spring downward, you are applying a force that stretches it, but let go, and the spring bounces right back up. This is elasticity in action. The ability of materials to behave elastically is due to the forces holding their atoms together. When a force is applied, it changes the distances between these atoms, but only up to a certain point. Elasticity is an essential property of many materials we encounter daily, from the rubber in car tires to the steel used in buildings. It ensures that objects can withstand deformation and maintain their structural integrity. Every material has its limits. Stretch a rubber band too far and it snaps. This breaking point is called the elastic limit. The elastic limit is the maximum amount of stress or force a solid material can withstand before it undergoes permanent deformation. Beyond this point, the material won't return to its original shape. Think of a car suspension spring. When a car goes over a bump, the spring compresses, absorbing the shock. As long as the force from the bump doesn't exceed the spring's elastic limit, it will return to its original shape, ensuring a smooth ride. However, if the force is too great, the spring might deform permanently, affecting the car's handling. Understanding the elastic limit is crucial in engineering and material science. It allows us to design structures and objects that can withstand the stresses and strains of everyday use without breaking or becoming permanently deformed. In the 17th century, Robert Hooke, an English scientist, discovered a fundamental relationship between the force applied to a spring and the extent to which it stretches. This relationship is now known as Hooke's law. Hooke's law states that the force required to stretch or compress a spring is directly proportional to the distance the spring is stretched or compressed. This relationship is represented by the formula F equals negative kx, where F is the force applied, x is the displacement, change in length of the spring, and k is a constant known as the spring constant. A common example of Hooke's law in action is a spring scale. When you hang an object on a spring scale, the spring stretches. The heavier the object, the more the spring stretches. The scale then converts this stretch into a weight reading based on Hooke's law. Hooke's law is a fundamental principle in physics and engineering, forming the basis for understanding the behavior of elastic materials under stress. It is used in various applications, from designing shock absorbers and car suspension systems to analyzing the behavior of structures like bridges and buildings. Section 4. Young's modulus. Measuring a material's stiffness. Not all materials are created equal when it comes to elasticity. Some, like steel, are very stiff, while others, like rubber, are more flexible. This difference in stiffness is quantified by a property called Young's modulus. Young's modulus, often denoted as E, is a measure of a material's stiffness or resistance to deformation under tensile or compressive stress. It represents the ratio of stress to strain in a material. A higher Young's modulus indicates a stiffer material. The formula for Young's modulus is E equals stress divided by strain, where stress is the force applied per unit area and strain is the change in length per unit length. Consider the steel cables supporting a suspension bridge like the Golden Gate Bridge. These cables experience enormous tensile stress as they support the bridge's weight and traffic. Steel's high Young's modulus ensures that the cables stretch only minimally under this stress, maintaining the bridge's structural integrity. Young's modulus is a crucial factor in structural engineering, helping us choose the right materials for specific applications where stiffness and resistance to deformation are paramount. Section 5. Modulus of rigidity. Resisting the twist and turn. While Young's modulus quantifies a material's resistance to stretching or compression, the modulus of rigidity measures its resistance to twisting or shearing forces. The modulus of rigidity, also known as the shear modulus and denoted as G, quantifies a material's resistance to deformation caused by shearing forces. Shearing forces act parallel to a surface, like spreading a deck of cards by pushing the top card sideways. The formula for the modulus of rigidity is G equals shear stress divided by shear strain, where shear stress is the force acting parallel to the surface per unit area, and shear strain is the deformation caused by the shearing force. Imagine a steel motor shaft transmitting torque. The shaft experiences torsional stress, a type of shear stress, as it rotates. A high modulus of rigidity ensures that the shaft twists minimally under this stress, allowing for efficient power transmission. The modulus of rigidity is essential in designing structures and components subjected to twisting or shearing forces, such as drive shafts, gears, and aircraft wings. Section 6. Bulk modulus. Holding strong under pressure. Imagine diving deep into the ocean. The immense water pressure at those depths could crush an ordinary object. However, submarines are designed to withstand this pressure thanks to materials with high bulk moduli. The bulk modulus, denoted as K, measures a material's resistance to compression from all directions, such as the pressure exerted by a fluid. It quantifies how much a material's volume changes under a given amount of pressure. The formula for the bulk modulus is K equals negative V times the change in pressure divided by the change in volume, where V is the initial volume of the material, dP is the change in pressure, and dV is the change in volume. Submarines are built with materials like high-strength steel, which have a high bulk modulus. This property ensures that the submarine's hull can withstand the immense hydrostatic pressure of the deep sea without collapsing. The bulk modulus is crucial in designing underwater structures, pressure vessels, and even understanding the behavior of sound waves, which are essentially pressure variations traveling through a medium. By understanding these elastic constants, engineers can predict how materials will behave under different types of stress and choose the most suitable materials for specific applications. From bridges to buildings, airplanes to automobiles, our understanding of elasticity shapes the world around us.